So can everyone see the screen, hear me just fine, etc.? All right, so can you hear me? Or is it just softer, something like that? Alrighty, I guess we get started. The topic for this week is going to be probability. I think it's also going to be including a little bit of counting because these two topics are like really close together, like closely related. So I guess you could say that like things, well, you could say that problems that involve probability often involve counting as well. So we start off with just a simple definition of probability, which is the number of desired outcomes over the number of total outcomes. And I guess this can be visualized in a lot of ways. So like if you're rolling a dice and you want to get a 1, there's only one possible outcome that's desired, which is the 1, and a total of 6 outcomes, which is the numbers 1 through 6. So your probability of rolling a 1 is just 1/6. So that's the most basic way of defining a probability, and we can use a definition to, I guess, solve more complicated problems. So these problems are really common in ANC tests. So yeah, that's kind of why I want to go over them. And mainly, these types of problems are really straightforward, and the only thing that you have to be able to do to solve them is just you have to be precise and like understand what you have to actually count in the problem. So as well, they are kind of easy to mess up. So it's pretty nice to check your work, especially with counting probability problems. So I guess the basics of combinatorics that I do want to go over is the number of permutations and objects is n factorial. And by permutations, I just mean the number of ways to order n objects. So if you have like 5 people in a line, then the number of ways to order them is 5 factorial. And this factorial symbol just means just n times n minus 1, n minus 2, times all the way to 1. I think I did go over this in a couple of weeks ago, but that's like definition of factorial, and the way you can think about it is that there are n ways to choose for the first spot, n minus 1 objects left for the second spot, and n minus 2 left for the third spot, and so on until there's only 1 object left for the last spot. And so yeah, that's really just permutations. This is like super logical, so you don't really have to like remember it, even though it's kind of simple. Next is combinations, and this is really important to know just in general, even like not in probability, and just straight up counting. Combinations are used in most problems, and it basically just says n choose k is equal to n factorial over k factorial times n minus k factorial. The factorials have the same definition as above, and the symbol n choose k just represents the number of ways to choose k distinct objects out of n total objects, and this does not include and this is when all objects are distinct. So if, and in most cases all your objects like are not the same, then you can use this. And also the order of the objects that you choose does not matter. So if you're simply asked to just choose 2 things, it doesn't matter if you chose this thing first or this thing second, then you have to use combinations. Otherwise, it would just be like an example permutation. Although you wouldn't have like the entire factorial part, you'd only have like the first some number of terms in the product. But yeah, just explaining with variables and stuff isn't really the easiest. So I think when we do get to problems using this, it'd be clearer to just see how it works there. Okay, so there really wasn't, it's kind of hard to give like a broad description of everything. So I kind of like split types of problems into like different methods that you could use. And so the first method I want to talk about is casework. And this one is going to be the most universal method and probably the most common one. And it's exactly what the name says. You make cases where you think of like all the possibilities for something and then calculate for each of the possibilities and add them all up. So this is kind of like brute force. And an example problem where you flip a fair coin 5 times, what is the probability that you never flip 2 heads in a row? So you can use casework for this. And when you're using casework, you have to first decide what you're going to do cases on. And I guess for this one, I'm just going to do cases on the number of heads you flip because this is talking about probability that you never flip 2 heads in a row. So it's going to be a lot easier when you know how many total heads you flipped. Okay, and before I go into that, I also want to write that the probability that you're going to find is going to be the number of like cases in which you have no 2 heads in a row over 2 heads in a row over like all possible flips. And basically, since you're flipping a fair coin 5 times, you're going to be 32 possible outcomes where each of the 5 flips can have 2 different values, heads or tails. So 2 to the 5th is 32, which means that it's like just you count the number of ones with not having 2 heads in a row and divide by 32. And so if we do casework, if there's 0 heads, then it's not possible to have 2 heads in a row. So this is just 1, as in there's only 1 case in which you only flip 0 heads, which is all tails. This 1 head, again, it's not possible to have 2 heads in a row. So this one would be 5, because you can have the 1 head you flip be the first coin, the second coin, the third coin, the fourth coin, or the 5th coin. So those are the 5 options. So there are only going to be 5 for this case. Next, we have the probability with 2 heads. And with this, we can do this in multiple different ways. I think I'm going to just use complementary accounting here, which since there was a good introduction for it, where we can count the number of cases where you flip 2 heads and the 2 heads are in a row, and I subtract that from all the possible cases with only 2 heads. So either way, what you can do is just, for one, actually, no, not think about it. I'm not going to do that. I think that it's I'm better off just doing that in the next section. I can just show you how you can brute force this. So if you have 2 heads, you can just assume that the first one's heads, as this is just like casework basically. And if you don't want any of them to be consecutive, you can have something like heads, tails, tails, or the heads can be a little bit further apart, or heads, tails, heads. And these are all the cases where the first one's heads. And if the second one is heads, then you have these ones, these 2, and then if the third one's heads and you don't have any like heads after or before it, then it would just be tails, tails, heads, tails, heads. So that means there are a total of 6 here, because we can just list out the 6 that work. And it's pretty clear because we did it systematically that there is no more other ones. So that's it for this case. And the last case where you have 3 heads, there's only one way to do this: heads, tails, heads. So this contributes 1 as well. And since if you have 4 heads, then you're guaranteed to flip at least 2 in a row. You can verify that. Right now we just add everything up. So it's just 1 plus 5 plus 6 plus 1 over 32, or 13 over 32. So the main point of this problem that I chose to put here is just to demonstrate how casework problems generally are solved, where it's kind of, you can think of it as just systematic and straightforward. There aren't many tricks. You just have to count everything, consider all the cases, and that's really it. So casework is pretty simple, but you just have to be precise with it, and yeah, that's really it. So next is complementary accounting, and this is where you count the opposite of what you want and then subtract from 1. And this takes advantage of the fact that the sum of all like the possible probability outcomes of something is going to equal to 1. So I think of it like the probability of rolling a 1, or probability of rolling a 2 or 3 or 4 or 5 or 6. They're each 1/6 on their own, but when you add them all up, they equal to 1. And this is because the total number of desired outcomes, when you sum them over all possible outcomes, is just equal to all possible outcomes. So that's why you can just subtract from 1 here. So an example problem is, let's say A, B, C, D, E are sitting in a row. Anyways, such that A and B do not sit next to each other. So this isn't exactly using probability, but it still uses something called complementary counting. And complementary counting is exactly like complementary counting and probability, where you can count the total number of ways for them to sit in a row, and then subtract all the ways in which A and B do sit next to each other. And then that's when you subtract it, you get all the ones that they do not sit next to each other, because there's no other case besides they do or they do not. So from the permutation formula, you can see that there are 5 factorial or 120 ways to have them stay in a row. And then for like them to have A and B sit next to each other and them sit in a row, you can think of A, B as a block or a single person. So then that would just be like 2 times 4 factorial ways for them to be able to sit next to each other, and all 5 of them are in a line. And that's because if we consider A and B to be next to each other, then we can just merge them together as 1 person. So now you're left with 4 people, and then that's 4 factorial from the permutation example. And then we're going to either have A, B, or B, A in the block, because the block doesn't specify the order. That's just an extra times 2. So then this evaluates to 48. And then the final answer would just be 120 minus 48, or 72. And the reason why you would use complementary counting in some cases is that it's sometimes easier just to calculate the complement. It's like more of a, using complementary counting is more of like a decision where you have to see the problem and evaluate whether or not you think it would be easier just to find the opposite. So yeah, there's really nothing else for complementary counting. All right, this next part I'm not sure. Okay, geometric probability. So this one is pretty rare, but also kind of easy to identify. And usually it has two different variables and it has some closed intervals and some relationship. So to solve, you graph it in a coordinate plane, so two-dimensional plane, and you find the ratio of areas. So an example is if A and B each choose real number from interval 0, 1, what's the probability that their numbers differ by less than 0.5? So if you approach this problem without using a geometric probability, you'll see that it's pretty difficult to solve because some numbers will have different results than other numbers. For example, if you choose 0.5, then the other person can choose any number in the interval. But if some other person chooses 1 or 0, then they can only choose from half of the interval. And so if we let the two numbers chosen be x and y, then we know that the absolute value of x minus y is equal to 0. Or not equal to, is less than 0.5. And this is just two lines with y is greater than x minus 0.5 and y is less than x plus 0.5. Since these are just the two separate cases in absolute value. And then we also have x and y are within the interval of 0, 1. So this is very graphable. Like when we have interval 0, 1, it's just think of it as a unit square. So 0, 1, 1, and like that. And this one is 1, 1. And the two lines that we have, when we graph them, y is greater than x minus 0.5. That's like here. And then the other one, y is less than x plus 0.5. That's here. And then these intersection points are going to be 0.5 and 0.5 here and 0.5 here as well. And then since these are actually inequalities, the first equality is greater than, so it means above this line, and the other one's less than, which means it's below this line. So then the entire graph, you would say, refers to this middle section over here. And the entire, like, all possible outcomes, that's just this square. So the probability would just be the area of the red section over the area of the entire square. And we can just find the area of the red section by subtracting these two triangles on the side. So this is just 1 minus, and the area of these two triangles is going to be 1/2 squared all over 1, which is equal to 3/4. And note that I wrote 1/2 squared since I just combined the two triangles into a square. So it's 1/2. So that's why I wrote it like that. Either way, that means that the answer is just 3/4, and that's really it. So, like, the main reason why this method works is because the graph itself just represents a collection of points, and essentially any point within the entire square refers to a unique ordered pair of values, x and y, and since all like x, y within the square represent all the possible pairs of numbers that they could have chosen, we just simply have to see where these x, y are within the square. So yeah, just remember that. I don't know if my explanation was very good, but geometric probability, you should at least understand just how the method works. All right, so I really do like this kind of problem because you don't see it too often, but it does have cool graphical representation. So after that, are infinite geometric series, and honestly, this one is very, very, very uncommon. So I might not talk too much about it, but essentially this is a geometric series. It's just like where each term has a common ratio with term before it. So something like 1, 1/2, 1 or 1 plus 1/2 plus 1/4 plus 1/8 plus all the way to like to infinity. And this is an example of a geometric series with common ratio 1/2. And all this really says is that the sum of the infinite sum is going to be equal to the first term over 1 minus the common ratio, which is r, or 1/2, which is equal to 2. And this only works if the common ratio is less than 1. So this is just something that you'd only use if you have some kind of game where you have two people taking turns doing something with a certain probability, and the game can technically go on into infinity, but it doesn't because there's like a fixed probability.
Excuse me, but what's the R?
R is what you call the common ratio.
Oh.
So it's like when you divide the term by the term before it, 1/2 divided by 1 is 1/2, 1/4 divided by 1/2 is 1/2, 1/8 divided by 1/4 is 1/2, and so on. So if you look at like the general variable expression of a geometric series, you can think of the first term as just a variable like a. Every term is just a times r, a times r squared, a times r cubed, a times r to the 4th, so on, and into a times r to like the infinity. And because of the constraint that the absolute value of r is less than 1, that means that like each term is getting smaller and smaller. So that's why the entire series does converge. Okay. Again, I think I do talk about series in more depth later, although it might actually be something I'm looking over. But either way, the only reason you'd actually need to know this, specifically pertaining to probability, is for a problem like the one underneath it. So like if A and B are playing a game with a weighted coin that comes up heads with probability 5/8, and A wins if he flips heads, and B wins if he flips tails, those are probably that B wins. And basically they take turns until one of them wins, which means that it can go to infinity. And yeah, so then the way you would do this would be to find like all the ways B can win. So B wins if A does not flip a heads first. So that's 3/8 times B flipping a tails, which is also 3/8. And this is probability he wins on the second turn or his first turn. But what if he doesn't win in this first turn and he wins on the second turn? That means that A couldn't have won on this first turn either. So that means A also does 3/8 for not flipping heads. Then B has a 5/8 chance of not flipping tails, and A has another 3/8 chance of not flipping heads, and then B has a chance of 3/8 of flipping tails on that fourth turn. And you can kind of see that this logic can be applied to any number of terms afterward. So this would be like a geometric series, and the first term is 9/64, and the common ratio would be 15/64. So yeah, you can actually check that for any like case of number of terms, it's just going to be 9/64 times 15/64 to some power. And you can think of it like 15/64 is the chance that for like each of them flipping, neither of them win. So then that one's just repeatedly multiplying by itself until you get to the turn where B does win. And the turn that he does win is 9/64. So that is just a way to logically show that
All the notes are on Google Classroom.
Yes, they are. Okay, they are on Google Classroom.
Notes are there.
So yeah, if you do want to follow along or anything like that, you can always see them there. So yeah, now you can just simply plug into the formula A over 1 minus R. So A in this case is 9 over 64, and R is 15 over 64. So it's 9 over 1 minus 15 over 64, over 64 here. And this is just 9 over 64 over 49 over 64. So it's equal to 9 over 49. So yeah, that would just be how these geometric, infinite geometric series problems would work. But you don't see them too often, so just know you can just keep it in the back of your mind. But yeah, I think that should be it for the. Okay, that's it on the notes. I did actually want to talk about one more type of problem, and it's on the note sheet. So if you want to just write it down on your own or something. So this one's called conditional probability, and this one it's a little bit different from all the others, is because it modifies what your denominator is going to be. And what I mean by that is that usually when you have a conditional probability, it says you're given something already happened. Given something, find the probability that something else happens, and that something else is related to that. So one example I like to use for this is if on like a simple level, for example, let's say you're rolling a pair of dice, and I guess we're just adding the 2 dice together to get some final value. So rolling 2 dice and adding them. So a conditional probability problem would ask something like, what is the probability that you rolled at least 1 5 given that the final sum was 10? So one problem would be like, given sum equals 10, given sum equals 10, what was the probability of rolled a 5? And the way you would approach a conditional probability problem is find the probability of this, and then find the probability of rolling a 5 and having a sum of 10. So then find the probability of both the previous and the new one combined, and then we divide those. So example, so I can solve this problem, for example, if the sum is 10, we know the probability of this happening is 1 over 12. And this is because your cases are 4, 6, 5, 5, and 6, 4 for the 2 die. And these are like 3 ways to do it over 36 possible ones. So this probability is 1/12. However, the probability of rolling a 5 and getting a sum of 10, there's only one way to do that. So this is 1 over 36. So in your actual probability, or your answer to the problem would be 1 over 36 over 1 over 12, or 1/3. So you might notice that this probability is quite a lot higher than the probability of just rolling of these combined, and that's always going to be the case. And I do want to mention that you do get a different answer if you just take the probability of rolling a 5, because the probability of rolling a 5 just without this constraint, so the sum is 10, the probability is 11 over 36, and that's because of complementary accounting, which you can verify on your own. But essentially, conditional probability will give you a different answer. So you can't just find a single probability and use that as your answer, because it's wrong. So yeah, This was kind of a simple example, but I do hope it demonstrated that concept. Yeah, so what I like to do for these problems is the conditional probability problems usually use casework. So then when you do that, you just find all the cases where the sum is equal to 10, and there are 3 cases. And within the cases, only one of them has a 5 in it. So you have 1 out of 3 total, like one case here out of 3 total in the case. So that's 1/3. So that's another way you can approach that. Just make sure that you are actually using the first piece of information to solve the problem. All right. So that is all the types of problems I wanted to talk about. Next, we have some general tips, very general. Just identify the method to use. This is just complementary accounting. Yeah, don't overthink it, check your work. Exploit symmetry. I do want to talk about symmetry later, but so yeah, I think that's it. All right, so again, if you have any questions on anything I've gone over, you can feel free to ask. So yeah, I think after this, we can just go on to the problems. I think we can just go through them in order. There aren't really, yeah, there really isn't one I want to go over specifically. All right, so the first one, the 2 cubical dice each have removable numbers. The 12 numbers on the 2 die are removed, put into a bag, drawn one at a time, and randomly reattached to the faces of the cubes. And then the dice are re-rolled. Numbers on 2 top faces are added. What is the probability the sum is 7? So, as the key insight here is that a lot of this, they're removed, put into a bag, drawn out, and re-rolled. It's kind of a smoke screen. And the way you think about it is that even though you're doing all this stuff to the die, you're not really changing any of the probabilities relative to each other. You're not making one more likely than, you're not making like rolling one more likely than rolling 6 or anything like that. Everything still has like the same relative probability, if you kind of get what I'm saying. But what does change is that you're not actually just rolling 2 die and find the probability of 7. That doesn't work. So I think the easiest way to think about this is when you're rolling the 2 die that have already had the numbers reattached, you're not really in control of anything, right? So it's better to go back a step to when all the numbers are just in the bag. So everything's in the bag. And this action of rolling 2 die and finding numbers on top, you can just think of it as just picking any 2 random numbers out of the bag. And these are equivalent because, again, attaching the numbers to the die faces are completely random. So you can kind of assume that, oh, this face of the dice will always be face up no matter what I roll. So then you simply just have like whatever number ends up getting attached to that face when you pull them out of the bag and like attach them to the face of the cubes, that's what's going to be end up rolling. So this kind of takes like the 2 dice out of the equation and just makes it you're pulling 2 numbers out of the bag. Right, so that's kind of just the logic step of this problem. So this just becomes taking 2 numbers out of the bag. And handwriting. I want to note that there is no replacement. So after you take a number out of the bag, you can't get that exact same number again. And yeah, so now we can actually go to solving this problem. And it's kind of convenient that the number you have to find the sum is just 7. And it's convenient because 7 can be made using any of the numbers: 1, 6, 2, 5, 3, 4, and 4, 3, 5, 2, 6, 1. So in reality, to get a sum of 7, it doesn't matter what the first number you choose is. As soon as you choose that one number, the second number you get must be fixed. So for example, if you just randomly choose a number out of the bag, you get a 1. That means that your second number has to be a 6. And if you get a 2, second number has to be a 5, and so on. So this is like symmetric. And when it is symmetric like that, you can ignore the first number entirely. So the thing about it is just, you already know what the first die ends up as. Let's say it's a 1. Then you need the second one to end up as a 6, right? After you already moved the 1 that was rolled first, you have 11 numbers left in the bag, and 2 of them will be a 6. So then the final probability is just 2 over 11. And that's kind of it. So yeah, I guess just note that some of these problems, they look kind of complicated on the outside, but they do have really simple solutions. So, all right, I think we go to the next one. Bernardo randomly picks 3 distinct numbers from this set, and Sylvia randomly picks 3 distinct numbers from this other set, and they arrange them in descending order to form a 3-digit number. What's the probability that his number is larger than her number? And here is an example of symmetry that I want to talk about, where if Bernardo did not have the option of choosing 9 and just 1 through 8 for both people, then the probability that his number is larger is just going to be equal to like 1/2. No, it's going to equal to 1 minus the probability that they get the same number all over 2. And this works because of symmetry. The probability like they get the same number is like the middle ground, so to say. And like if they don't have the same number, then one of them has to have a larger number. And since they're both choosing from the same set of numbers, there's no reason for any one person to have a higher chance of getting a larger number. So their chance of getting a large number is just going to be the same. So that's why this 1 minus probability of them having the same over 2 is that. So this is like the probability if you can only choose from 1 through 8. But we also have to consider him choosing 9. And when he chooses 9, he automatically has a larger number. And this is because, well, the set 1 through 8 is never going to get a number as large as 900 as the number that I arranged in descending order. So we can just add plus probability of 9, probability of. So like we can just write like our answer like this, where we have the probability to choose the 9. That's like an automatic win. So we just have that as its own. And we have the probability he doesn't choose a 9 times 1 minus the probability and times the probability that he's larger and he had to choose from 1 through 8. So yeah. And you can see that this does like cover all cases because get to 9 and not get to 9 is like our complementary cases. But there isn't a case that's not within both of them. So yeah. I guess I can solve this. This P of 9 here, it's equal to 1/3. And this is because he chooses 3 numbers and there are a total of 9 numbers. So like he is like 3 over, they're like, if he chooses 3 numbers, 9 has a 1/3 chance of being there because, well, it's just 3 over 9. There really isn't any complicated way of saying it, but yeah, that's kind of just, if that makes sense. And then probably not getting 9 is 2/3, and 1 is probably the same over 2. We have to figure out the probability of getting the same number, and that just means that you ended up choosing the same 3 digits. And there are 8 choose 3 different ways of choosing 3-digit numbers all over there are 8 choose 3 total numbers that Sylvia could have gotten, and Bernardo can only have one of them. So like the probability of them being same is just 1 over 8 choose 3. And this is, I think I explained that a little bit wrong. Sylvia, if we assume Sylvia already chose a number, then there's just one number. Let's say she chose 8, 7, and 6. Then out of the 8 choose 3 numbers that Bernardo could have gotten, only one of them is the exact same. So that is the probability of 1 over 8 choose 3. And it's equal to 1 over 56. So then you can just write it like this. And this is 55 over 56 times 5 over 56 divided by 3 plus 1/3. And this is 55 plus 56, 111 all over 3 times 56, or 37 over 56. All right, that's a 7, not a 3. Yeah, things to emphasize from this problem. Symmetry. Use it to your advantage. That's kind of the only way you can actually solve this problem. And yeah, consider, I guess this is kind of cases too, where you have a 9, you don't have a 9. But that's it for this problem. All right, so next. 20, okay. This next one is, I guess, probability, but using variables. And that's a little bit different from what we've done before. So each of 2010 boxes are in a line, and they contain a single red marble. And the box in the Kth position also contains K white marbles. And she begins at the first box and draws a single marble, and then she stops and she draws a red marble. All right. So basically, the first box has 1 red, 1 white. The second box has like 1 red, 2 white, if I'm not mistaken. Yeah, and as for the probability that she stops drawing after exactly n marbles. So you can write piece of n in terms of n, and that's kind of the point of the problem. So this is just like 1/2 times 1/3. I'm sorry, not 1/2 times 1/3. It asks for like the probability that the first red marble you get is from the nth box. So we need all the marbles from the other boxes before it to not be red. So this happens like with n minus 1 over n chance, or k minus 1 over k if we're not. Yeah, okay. So it probably will look something like this, where we get to times n minus 2 over n minus 1, and times 1 over n. And this must be less than 1 over 2010. And essentially, this is just a very large telescoping thing where the numerator of the next fraction cancels with the denominator of the one before it. So this just becomes 1 over n times n minus 1. And this is just a simple algebra question. And if you solve it, you just get the smallest possible value of n here is 45, I believe. So that would be the answer. Actually, it might not be 45. I think it's 46. Wait, no, it is 45. Yeah. I wrote something a little bit differently here. The last term should actually be 1 over n plus 1 because the nth box has n plus 1 total marbles. So this is actually n times n plus 1. Yeah, so yeah, you guys see how to really be careful with these related problems. But yeah, so either way, answer is 45. It's just like shows that you don't actually have to have all the numbers to be able to solve a problem. You should be able to write out as like kind of a formula with variables. Yeah, all right. This next problem, just say it's kind of a lot of casework, and that's really it. So I don't really want to do the casework here. You can look up the problem, or you can do it by yourself if you'd like. But for the sake of time and like it's kind of tedious, I'm just gonna move on from it. So yeah, the next one. Suppose that 1 of every 500 people in a certain population have certain disease. A blood test is available for screening for this disease, and yeah, something about false positives. Yeah, it's kind of a long problem. You can read through it, but essentially, this is kind of an example of conditional probability, where you're finding the probability that the person like has a disease, given that they had a positive test result. So what this means is that you can't just say, oh, it's 1 over 500, because 1 of every 500 people have the disease. That's not it, because you won't have 500 positive tests out of all those 500 people. And so as a conditional probability I went over, this is just going to be the probability that they do get a positive. Actually, for this one, it's easier to use actual number instead of probability. So what I mean is that just assume that there are 500 people in the population. But this just makes the numbers easier. So you have 500 people in the population. That means one person has the disease. So that person is going to be a positive test. But of like the 499 other people, 2% are going to also have a positive test. And this is roughly 10 people. If you see the problem, it says which of the following is closest to. I guess I forgot to put the answer choices in. Kind of sucks, but it is what it is. You can always see the answer choices if you look at the problem. But 2% of 499 is around 10, since 2% of 500 is exactly 10. So then the conditional probability is just 1 over 1 plus something that's around 10. So this should be around 1 over 11. And that's the answer. And I guess the cool thing that this problem actually touches upon that's not really super math related is something called the false positive paradox, where even if like an event is super rare, and it's more likely for any positive that you get to be a false positive than to actually be a real positive. So like if you see here, if you do get a test and it's 98% successful, which is a really high or a seemingly high percent, you're not actually very likely to actually like have the disease. So yeah, if you're interested in that, you should look up the false positive paradox. It's pretty interesting. But yeah. All right, so next is this. Chloe chooses a real number uniformly at random from the interval 0 to 2017. And Laurent also chooses a real number from this larger interval. What's the probability the number is greater than Chloe's number? So I like this problem because you can solve this using 2 different methods. First method is geometric probability. I think this one is pretty easy to see from just the similarity from this problem to the example problem that I gave. And the other one would be using symmetry. And you can see that this is kind of similar to the earlier problem that we did with Bernardo and Sylvia. So both ways do work. Geometric is kind of pretty though. So if you let Chloe, for example, let Chloe be the X and Laurent be the Y, you'll have like a rectangle with side lengths of like 2017 and 4034. And the line is just Y is greater than X. So this just looks like this. And it's just whatever the section above the line is. So here, since this is Y greater than X, this point here is also 2017. And just so happens the numbers they gave, 2017 is 1/2 of 4034, which makes the calculation super easy. And probably it's just 3/4, because this is half of the height. This is the entire base. So it's like 1/2 times the base times 1/2 since it's a triangle, or 1/4 times the area of the rectangle. So then to find it, probably just 3/4. And you can also use probability symmetry, sorry, for the other case. And this is like you either have Laurent choose a number between 0 to 2017, or a number between 2017 and 4034. And since any number is equally likely, these intervals are the same length. So probability of each of these happening is 1/2. And then in the second case, the final is 1/2 because any number that chooses here is guaranteed to be greater than any number that Chloe can choose. And note that we don't consider the case where they both choose the same number, because there are an infinite amount of real numbers in these intervals. So that one specific case where they have the same is just going to be like effectively 0 in the scope of infinity. All right. That's also why you don't consider any points on the line when you're calculating area, because the line has area 0. And then the second case where she chooses from 0 to 2017, there's simply just a 1/2 chance that she's larger, because they're both choosing from the same like set. So this just becomes times 1/2 or 1/4. And then we add them, it's also equal to 3/4. And you can actually kind of see how the geometric thing can like visually represent this. If you draw a line right here at like 2017 mark, you see that this is like 1/2, or the second case, and this here is just the first case. So yeah. Again, cool applications. All right, so okay, next is this. This is actually just the geometric probability question that I might use an example, just with different numbers. So since I've already got over a geometric probability problem, I'm also going to leave this one to you as extra practice if you do want it. There is really nothing different from the other problem, just different values. All right. This 2018 10A number 11 problem. When seven fair standards 6-sided dice are thrown, probably the sum of the numbers on the top face is 10 is something. And what is this n? All right. So with this problem, it seems to be a lot of casework. So you'd have, since you have 7 die and the numbers sum is 10, the actual values that you have, well, class ends at 8 p.m. so you won't be leaving early, but okay. Okay, but either way, what I'm getting at here is that since you have 7 standard die, you can just do casework on how many ones are rolled. So if you have 6 ones rolled, then you have to have 6 ones and 1 4. Then if 5 ones, then it's like 5 ones, and you have you roll 1 and 4 on the 2 other die, or 2 and 3 on the 2 dice. If you have 4 ones, then that means that you have 3 die sum to 6, 3 sum to 6. With 3 ones, you have like 4 summing to 7, and none of them can be 1. This is not possible. And obviously, anything below that's not possible either. So in this case, there's only just 2, 2, 2, by the way. So there's only one case here. So I'm not gonna like completely solve the problem, but this is how you could do cases. And from these cases, after you just count how many total ways are possible, and you just simply add them, and that's just n, because the denominator is 6 to the 7th, which is the total number of possible ways anyway. So like 6 to the 7th is just 7 die and 6 possibilities for each die, 6 to the 7th. All right, so if you do want to finish this problem by yourself, feel free to. Again, this is just another example of casework. All right, so I think I left 2 problems undone here. And here's the challenge problem. I actually want to do the challenge problem this one, since it is kind of relatively easy as I marked. And we don't usually get to do these. So you have like 3 minutes, that's enough time to do it. So real numbers x and y are chosen independently and uniformly at random from this interval. Was it probably the x, y, and 1 other sides of an obtuse triangle? So first, a few observations. This is a geometric probability problem because, well, it's you have 2 numbers x and y and a closed interval 0, 1. So that's like the most straightforward way to do it. And next, x, y, and 1 are the side lengths of an obtuse triangle. So what does this mean? I'm not sure how many of you are actually familiar with this, but I think this is part of something I did talk about in the earlier weeks. So since x and y are between 0 and 1, we know that 1 has to be the longest side of the obtuse triangle. And the relationship between the side lengths to make this an obtuse triangle is that x squared plus y squared must be less than 1. And this kind of looks like Pythagorean 1 squared, but 1 squared is 1. This kind of looks like the Pythagorean theorem, and it really is. And I guess the way you would show this is related is by the law of cosines. And this is because the cosine of an obtuse angle is going to be greater than 1. So like that term in the law of cosine is going to be positive when x squared plus y squared is less than 1, and that's how it works. So yeah, either way, this relationship is very necessary to know for an obtuse triangle. And again, law of cosines is in the notes about like triangles, I think, some number of weeks ago. So yeah, with this, we can solve the problem. We can, the 0, 1 is just going to be a unit square, 0, 1, 1, 1. And x squared plus y squared is less than 1. This happens in this part to be the quarter circle, because again, this is the graph of a circle with radius 1 center at the origin. We'll only look at case where x and y are between 0 and 1. So this is just the circle over the square. And the area of the circle is going to be pi over 4, as that's like 1 squared pi divided by 4. And the area of the entire square is just 1. So the probability is just pi over 4. So yeah, that was a neat way to do this problem, where you use geometric probability to, I think it's the only way you can really solve it. And yeah, it's pretty cool how you can relate these obtuse triangle part to pi. But yeah, that's it for this problem. That's also it for this week. Yeah, so you guys can leave if you don't have any questions. I'll hand it over. Oh wait, you actually do make a good point here. I actually forgot about that. Good job. Oh well, I'm sure if you look up the answer, you'll see that I was wrong. But yeah, you are actually correct. X plus y does have to be greater than 1. I forgot about that. But we're basically, yeah, triangle inequality. So I guess the method still stays the same here, where you just draw the line x plus y greater than 1. That's here. And the area is just the sector. And we did find the area of a sector before, so it should actually be pi over 4 minus 1/4. Yeah, 1/4 over 1. So yeah, should be pi minus. I believe it should be pi minus 1 over 4 now. That makes sense. Nope, it doesn't. It's pi minus 2 over 4. Okay. All right, yeah. So if you are staying and watching, yeah, the answer was actually pi minus 2 over 4. Yeah. Okay. Well, I made a few mistakes today that I should not have made, but well, thanks for pointing that out. So yeah, if there's anything else, feel free to say it, but we're not going to be doing anything more today.
Thank you.